Welcome back to part 2 of vector components. In this video, I'm going to specifically show you how to take a vector, a 2D vector, and break it down into its horizontal and vertical components, its x and y components. Now, why do we do this? Because when we analyze motion, we oftentimes look at the motion in either one axis or the other one. Why? Because the vectors in the horizontal and vertical directions do not affect each other, which means these components of any vector work independently of each other. When we do calculations involving horizontal vector components for 2D vectors, we will deal with them separately and not together. This will become relevant as we show you how to add vectors. Here I have some examples of vectors. Now, when I say breaking a vector down in its horizontal and vertical components, I mean that a vector in a 2D space will have part of its motion in the x direction, meaning along the y-axis or horizontal direction. It will have part of its motion in the y-axis or the vertical direction. What we want to do is find out how much it goes up and down or in the vertical direction side versus along the horizontal direction or in the x direction. To set up a coordinate system, imagine that I have this vector here in an x and y or horizontal and vertical coordinate system. How do I break a vector down? First, I imagine I draw kind of like a triangle, a right triangle that encapsulates this vector itself, starting from its base. Imagine that you have to take two separate motions to achieve the same arrow, this vector over here. First, you have to go down, then you have to go right. The going down and then going the right describe the particular components of the vector itself. So what I'm going to use purple for vertical, green for horizontal. If I go from the beginning, if I go down vertically, this is my vertical component. This is my y. Going horizontally will be my x component or my horizontal component. You might even notice that it doesn't matter which direction you take, it will still lead you to the final result. But regardless of which direction you go to achieve this final vector over here, notice that these lengths are all the same. The horizontal lengths are the same, the vertical lengths are the same, the components in either case are the same. Let's take a look at B. And of course, try this yourself first, pause the video before me showing you how it's done. Again, imagine having a triangle. Imagine this vector encapsulating a triangle. You have first in this case, I have its horizontal component first, drawing that side of the triangle, and then drawing this side of the triangle, which is my vertical component. And of course, I can always do it the other way around. I go up first, and then I go left second. C is another example, and again, you can try this yourself, but I'm going to go a little bit faster now. What I'm going to do, I'm going to skip that middle step and say, well, I start from my base, I go as far left as the edge of my arrow hits. I draw my horizontal vector component here, and then this is my vertical one. And if I go the other direction, I have my vertical one first and my horizontal one second. But no matter which case it is, this 2D vector has a specific amount of motion in the x direction, specific amount of magnitude of motion in the y direction. That makes up the 2D vector. And what we've done is deconstructed it into its separate horizontal and vertical components. So we've broke this down qualitatively. How do you do it quantitatively? Notice that all of the triangles were right triangles, which means if you know an angle, you know a side length, you're going to be able to use SOHCAHTOA to solve for all of the sides of the triangle. And of course, you can even use Pythagoras to do that as well. Although you would probably prefer SOHCAHTOA because that usually decreases amount of miscalculations, error carried over from your previous questions. Let's do an example together. Here I have a vector. It seems like it's going 123 meters at 33 degrees north of east. So to break this vector down into its horizontal and vertical components, first of all, I draw my triangle. It has a horizontal component and it has a vertical component. I'm going to calculate these components separately. Let's start with the x direction. Along my x direction, I have 33 degrees as my angle. I want to know this adjacent side of the 33 degrees, and I know the hypotenuse is 123 meters. If I want to find the x, this is adjacent to my hypotenuse. I look, oh, I need ka for this case. I need cosine. So cosine of 33, this is equal to my adjacent, which is my x, and my opposite, which is 123 meters. I solve for the x, which gives me 123 meters times cosine of 33. Punch this into your calculator, and I get 103 units. 103 as my magnitude, and in this case is looking for meters. I am going to write 103 meters, although if I have to do significant figures to two significant figures, I'll have to round this down to 100, which I can express as 1.0 times 10 to the power of 2 meters. Now for the y direction. As for the y component, you take a look. I have my angle, 33 degrees. I need to find y. I have my hypotenuse is 123 meters. I need the opposite and the hypotenuse. I have the hypotenuse, which leads me to use SOH in this case. So for SOH, this is sine theta, which is 33, equals opposite, which is y, and over hypotenuse, which is 123 over 123 meters, and then I solve for y. Y then gives me 123 meters times sine of 33. I punch this into my calculator, and this gives me 66.99. And this is totally gonna round to 67 meters. Oh yes, and one other thing that you have to be very careful, even though if you're breaking things down into their components, all vectors have direction. So I will have to write the direction of all of these components, starting from the 103 meters. This is 103 meters going east. So I have to include this in my response. Vectors have both magnitude and direction, which means you have to include the direction for all of them. This is 67 meters north. Here is the example for us together. There is a few ones down below. I will do another one with us and then quickly go over the other ones. Here we have 170 meters 88 south of east. Oh look, this is using everything we've learned up till now, including the naming. So south of east generally is going to be in this direction. This is 177 meters 88 south of east. So I'm going to draw east first from my base, and then I'm going to draw the south, which is second. 770 meters is this, and my angle is 88 degrees. Oh, that's crazy talk. Okay, so then I have my x and then my y component, which I'm going to try to find. As for my x component, this is my adjacent side of 88. Adjacent hypotenuse means cosine. So this is cosine of 88. This is equal to adjacent, which is x, over hypotenuse 770 meters. Then solving for x by multiplying both sides by my denominator. This gives me x is equal to 770 meters times cosine of 88. And putting this into my calculator, this gives me 26.87 meters, which will then round to two significant figures, or 27 meters. For the y direction, I have or the y component, this is my opposite over my hypotenuse, meaning so in SOHCAHTOA, this is sine of 88 equals to my opposite, which is y, over my hypotenuse, 770 meters. Okay, and then solving for the y, meaning multiplying both sides by my denominator, and then solving for y equals to 770 meters times sine of 88, which gives me 769, which is very close to 170. Unfortunately, this does round to 770 meters south. It's really weird. I know, it's the rounding that causes this kind of confusion, because that's really pretty much this original vector itself. Oops, and I forgot the direction for this one. So now you have the two components, 27 meters east and then 770 meters south. Here I would give you the opportunity to try example 8 and then example 9. Example 8, and I'll quickly go over it. Same thing with example 9 to follow. Here is the finished work for this triangle. Over on this top, I'm covering how you can find the x component. The bottom is looking at the y component. Again, you start with drawing out your vector, labeling the x and y component size so you can visualize where the angle goes for your right triangle, and then you can work with SOHCAHTOA to figure out x and y's. Starting with the x over here, I have this is adjacent over hypotenuse, so this is cosine 12 equals to adjacent over the hypotenuse. Solving for the x gives me 1.2 meters per second squared west. So little fishy, but this angle is probably very small, which is why you have a very large west component. In the y direction, so this is this guy over here, you have sine 12, so this is opposite over hypotenuse. So sine 12 is opposite y over the hypotenuse, 1.2 meters per second squared, and then solving for y, giving 0.25 meters per second squared north. And here is the example number 8. If you struggle with example number 8, well, you give number 9 a try. Pause the video, and again, I will go over example 9 just like example 8. Here is the finished example of number 9. This one was a little tricky because it looks a little different than the other ones. 115 meters per second at 55 degrees below the horizontal. So first drawing the vector, it will look like this. I first labeled the top horizontal being the ground. Imagine being horizontal, parallel with the ground. And then the vector being 55 degrees below the horizontal. So kind of coming down like this. This now arrow looks like this at a 55-degree angle, and 120 meters being the magnitude. I label the x and the horizontal as well as the vertical component side to make my right triangle, and then I went with the cosine and sines for x and y components. Starting with the x component, we look at, again, I need the adjacent, but I have the hypotenuse, which is adjacent x over hypotenuse, which is 120 meters per second, solving for the x, giving me 69 meters per second. As for direction, this is all very arbitrary. I just said right, because on the page it's towards the right. Normally, maybe if the directions were available, you would go with the directions. Otherwise, you can specify one yourself. As for the y direction, going down, this is the opposite side of 55 degrees, and having the horizontal, I did sine 55. This is equal to the y over the 120 meters per second. Solving for the y, I get 98 meters per second going down. That was the last example in this lesson. Hopefully you got something out of it, or you're feeling a little bit better with some of the questions. Otherwise, thank you for watching, and please get more practice as much as you can. Good luck, and see you next time. on the Lee channel.